In this lesson, we're going to be introduced to orthogonal vectors. We're not going to go into a lot of detail because the next several sections through the rest of this course will deal with orthogonal sets and orthogonal vectors. Since we're going to be spending quite a bit of time with orthogonal vectors, it's important to understand a little bit more about them than we know right now, which is essentially nothing. But orthogonal vectors are vectors that are perpendicular to one another. So as you can see in my picture, I have vector u and vector v. I've also drawn in vector negative v just for a later example in just a moment. But just looking at u and v, it does appear that they are perpendicular to one another. In order for us to know for sure, we can use the fact that two vectors are orthogonal if the dot product or inner product of u and v is 0. So I'm going to show you using u, which is 7, 7, and v, which is 2, negative 2, that if I did in fact find their inner product, that I would get 0. But where did that come from? How do I know that the inner product must be equal to 0? Well, if I look at my picture, it's clear that the distance from u to v should be the same as the distance from u to negative v. So essentially what I'm going to do is I'm going to find this length and square it, and this length and square it, and those two things should be equal to one another. So let's find out. Let's see what we can find out. The distance between u and v says u minus negative v. Sorry, the distance between u and negative v says let's take the distance u minus negative v, which of course means I'm adding. So essentially I have find the distance of u plus v. Square it. So the distance of u plus v would be u plus v and the inner product with itself, u plus v. Oops, not squared anymore. And using some of the properties that we know, I have that u with the product of u plus v, so the inner product of u with u plus v times u plus v, inner product. And again, doing a little bit of more of our properties, we've got u and u here, so I can say u, inner product of u and u, plus the inner product of u and v, plus the inner product of v and u, plus the inner product of v and v, which is essentially the length of u squared plus the length of v squared plus 2 u inner product v. If I do the exact same thing on the other side, so I'm going to be doing similar calculations over here. This is going to be u minus v, because that's how we compute the distance. And then that means, and then again, u minus v. I didn't do anything on that step. So this is u minus v product, u minus v. Sorry, my v's and u's are starting to look a little bit alike. And then again, doing that same, using those same theorems, using those same properties, I can say u times u minus v, u inner product of u minus v plus, minus v, and then inner product of u minus v. And we can see that this is very, very similar. So this is u with the inner product of u minus u with the inner product of v minus v inner product u minus, plus v inner product v. And so as we can see, what's happening is I have the length of u squared plus the length of v squared, and this time I have minus 2 u inner product v. And so essentially what we're saying is for these distances to be the same, these obviously are the same, these obviously are the same, we need 2 u inner product v to be equal to negative 2 u inner product v. And the only way that that's going to happen is if UV is 0, because 2 times something is not going to equal negative 2 times something unless that something is equal to 0. So that's where this comes from. So hopefully that helps you to understand just a little bit in a little bit more detail. Let's try this question. We're looking for which pairs of vectors are orthogonal. And again, when we're doing this, all we're doing is finding the inner product. So I'm going to take A, B and determine the inner product. So in this case, that would be 4 times 2 plus 3 times 0 plus negative 2 times 4, because again, that inner product just says multiply corresponding parts. You can certainly turn it into the transpose if you want, but I'm not ever going to do that. 4 times 2 is 8, 3 times 0 is 0, negative 2 times 4 is negative 8, and therefore my inner product is 0, and A, B are orthogonal vectors, which means if I were to graph these, which would be more difficult in 3 dimensions, but if I were to graph them, they would in fact be perpendicular. Now let's try AC. So again, AC would be 4 times 2 plus 3 times 0 plus negative 2 times 1, which gives me 8 plus 0 plus negative 2, which is 6. Clearly not 0, therefore not orthogonal. And last but not least, BC. BC would be 2 times 2 plus 0 times 0 plus 4 times 1, which gives me 4 plus 0 plus 4. Whoops. And that obviously is 8, and that is not 0, so A or B, C are not orthogonal.